Okay, you've seen them everywhere, right? Those absolutely incredible, sometimes mind-bending images that AI creates from just a few words of text. It really does feel like magic. But what if I told you it's not magic at all, but actually an incredibly elegant process? Well, today, we're going to pull back that curtain on the engine behind it all, the diffusion model.
So how in the world does that even work? I mean, how can a machine look at a field of pure random static, like an old TV screen when the signal goes out, and somehow, step by step, turn that chaos into something coherent and often really beautiful?
Well, the answer is completely counterintuitive. Get this. To learn how to create something, the AI first has to become an expert at destroying it. It learns to build a perfect image by first mastering exactly how to break it down, piece by piece, into pure noise.
Now, this whole idea came about to tackle a huge challenge in AI, something you could call the creative machine problem. The real question is this: how do you actually get a computer to make something genuinely new? Not just copying and pasting what it's seen, but generating something that follows all these complex, invisible rules to create a totally unique image.
People have tried a few different ways to crack this nut. Some of the earlier models, they tried to create a direct statistical map for what an image should look like, but they often ended up a little blurry or imprecise. Then came the famous GANs. You can imagine these as two AIs in a duel. You have a generator trying to paint fakes and a discriminator trying to spot them. It's a really clever idea, but that constant conflict makes them notoriously unstable and super tricky to get right.
So diffusion models took a totally different and honestly a more elegant path. Instead of this high-stakes duel, they asked a much simpler question. What if we just gave the AI a puzzle? A really simple one. Hey, I'm going to mess this image up. Your only job is to figure out how to fix it.
And this is that puzzle in action. So in step 1, we start with a perfect, clean image. Then step 2, we just add a tiny bit of noise. Step 3, we just do that again and again, hundreds of times, until we hit step 4, where the original image is just completely gone, lost in a sea of static. Now that's the easy part. The real challenge, was shown in step 5, is teaching the AI to learn the reverse journey, to perfectly undo every single one of those noisy steps to get all the way back to the original.
And that, right there, gives us our core definition. A diffusion model is basically a generative model that learns to create by reversing a gradual noising process. It's such a beautiful idea, right? If you can perfectly map the road from a clear image to total chaos, then you have also, by definition, learned the map to get all the way back again.
All right, so this whole process is kind of like a dance with two very distinct parts. To really get it, we need to look at both of them: the forward march into chaos, and then the carefully learned steps that lead all the way back to clarity.
So the forward process is dead simple. It's just a fixed recipe for adding noise step by step. There's no intelligence required here at all. But the reverse process, this is where all the magic happens. This is the hard part, where a massive neural network has to learn how to be the creative engine, figuring out precisely how to undo that noise at every single stage of the journey.
And here's the absolute genius of it. The AI isn't asked to guess the final, clean image right from the beginning. That would be incredibly difficult. Instead, it's given a much simpler job. At any given step, just look at the messy image and predict only the noise that was just added. That's it. That's the entire task. And that one simple task is the key to everything. See, by becoming an absolute expert at just spotting the noise, the model implicitly learns everything about the structure of a real image. It learns what a cat looks like by getting incredibly good at identifying everything that isn't a cat, in this case, all that random static. Now, it turns out this step-by-step process of adding and removing noise isn't just some clever computer science trick. It's actually grounded in a really deep and powerful field of mathematics, the math that describes how things flow and change continuously over time.
Think of this transformation from a clean image to pure noise as a kind of continuous flow, like a river. And it just so happens that the mathematical language we use to describe any kind of flow, whether it's heat spreading through a room or a planet's orbiting a star, is called differential equations. Now, you don't need to know the math, I promise, just that it provides the perfect rulebook for describing this entire process from start to finish.
And what's really cool is that this mathematical framework unites all the different flavors of diffusion models out there. A DDPM treats the process like a series of distinct movie frames, a score-based model is more like figuring out which way is downhill to get to the clear image, and flow matching tries to learn the exact velocity of that river at every single point. They're all slightly different approaches, but fundamentally, they're all just finding creative ways to solve the same underlying equation of flow.
Okay, so we have this really elegant theory, it's grounded in some serious mathematics, but how does that connect to the jaw-dropping creative results that have taken the world by storm? Why is this specific approach so uniquely powerful?
Well, there are 4 really big reasons. First, the quality of the final images is just unprecedentedly good. Second, the training process is way more stable and balanced than those old competitive models. Third, and this one is critical, that step-by-step reversal gives us a way to guide the process, like a hand gently steering it. And finally, that solid mathematical foundation gives researchers a clear rule book for making these models even better over time.
That control is something we call guidance. At every single step of the denoising process, we can nudge the AI. We can say, okay, remove the noise, but as you do, make it look a little more like a red house. It's like whispering directions to an artist with every single brushstroke, which gives us this incredibly fine-grained control over the final image.
Which really just leaves us with this final thought. Diffusion models have shown us that by understanding the path to total randomness, a machine can learn to reverse that path and find structure, coherence, and even beauty. So if we can teach an AI to find perfect order in pure chaos, what in the world is the next frontier for creativity itself?